Greetings, everyone. Today we're going to take a look at the rational zero theorem. For this, you'll definitely want to take some notes and follow the examples. A calculator might be of assistance for solving those examples, and of course, a writing utensil. All of the factoring we've done so far have been with polynomials that are factorable, that you are able to break down and break apart. But what happens if it's not factorable? Or what happens if you're not given a hint like we had in our X factor assignment today? Then what do? So in this video, we're going to find a way to solve polynomials that can't be factored and when you're not given a hint. Since we aren't given a hint, we need to find our own hint and become an educated guesser. We're going to use what's called the rational zero theorem. If you need some extra examples or extra assistance outside of this video, that's what you're going to look up, is rational zero theorem. Every rational zero has the form of P over Q. P represents the factors of the constant, or the end term, and Q represents the factors of the leading coefficient. So to make this as easy as possible, you'll want to make sure, as always, that your polynomial is in standard form. A couple of keywords to keep in mind are real numbers, rational, eventually we'll get into some irrational, and imaginary numbers. Let's take a look at this first example. Here we have the function f of x equals 2x cubed minus 5x squared minus 14x plus 8. It's got 4 terms, so my first inclination is to do factor by grouping. But if I try that process, it won't work out because this polynomial as it is not factorable. So that is why we are going to explore this process. Let's start off by finding the real zeros. Again, we want to use that PQ form. Take a look at the factors of the beginning and the end. Our constant has factors of plus and minus 1, plus and minus 2, plus and minus 4, and plus and minus 8. All of those come from our constant. Now we want to take a look at the factors of our leading coefficient, or 2. Plus or minus 1 and plus or minus 2. Now notice I said P over Q earlier, which means I may have some fraction combinations that occur out of these zeros as well. If I put each of these P factors over 1, I end up with themselves. So plus and minus 1, plus and minus 2, plus and minus 4, and plus and minus 8. Now if I take all of the P factors over 2, I end up with 1 over 2. That's a new value we haven't used. 2 over 2, which is 1. 4 over 2, which is 2. And 8 over 2, which is 4. So in this case, I only created one additional fraction factor by going through the P over Q process. So if we take a look, these are my possible zeros. We want to see which one of them can become our hint so that we can make this polynomial factorable. Let's continue with the example. As you can see, I have all of my possible zeros that we just found listed. To start off and see which ones work, all we're going to do is plug them into the function and see which ones give us 0. So I'm going to start off with 1. If I plug 1 into the function, and this is where you might want to use your calculator, If I plug all of that in, I do not equal 0. Therefore, 1 is not a factor. I'm going to try a -1 next and just go through my list of possible zeros. If I plug in -1 for all of my x values, try plugging it into your calculator as well, because you want to make sure you're using those parentheses correctly. When we plug this one in, we don't get 0. Doesn't matter what the value is, it's not 0. Let's plug in 2. If I plug in 2, unfortunately, again, I don't get equals 0. Takes a little bit of time, but don't give up. Let's keep going. Let's try -2. Notice that the signs will make a difference because cubing a negative versus squaring a negative is going to give me a different sign. Oops, that should be a -2. If we plug all of that in, we do end up with 0. So definitely make sure that when you plug that in your calculator, you are getting 0. So -2 is a factor. What do we do next? We still haven't found the rest of the zeros. Now, could I sit here and plug in every single number to get to 0? I could. That would be a very long process though. And sometimes our list is very, very long. So what we're going to use is some of the previous knowledge that we've gained over the last couple of weeks. We're going to use synthetic division, and we're going to put our -2 on the outside. We're going to put our integers on the inside. And let's go through the division process. Bring down your 2. 2 times -2. Add -9. -2 times -9. 18. We get 4. -2 times 4 is -8. And we get that 0. This again confirms that yes, -2 is a 0. So to be honest, I plugged in all of these numbers to see if they equal 0. I could also do synthetic division over and over again until I find a 0. It's up to you and what process makes the most sense. What's helpful is now I've broken down that polynomial into 2x squared minus 9x plus 4. This is a trinomial. So now I can use the AC method and factor it all the way down. We'll end up with a times c, put our b value here. Factors of 8, that could get me 9, are 1 and 8. I gotta watch my signs though, they both have to be negative. So this breaks down now into -1x and -8x. Oops, and that should be a plus 4. I've got my 4 terms, so now I'm going to use my grouping method. I can take out a GCF of x out of my first set of parentheses. I have a GCF of -4 out of my second set of parentheses. Now my GCF is 2x minus 1. If I divide that out, remaining is x minus 4. This process is what we've been practicing. And if I set each of those factors equal to 0, I now have my remaining zeros. This would give me x equals 1/2. And my second factor would give me x equals 4. So we have 3 zeros. We have our original -2, And then we just solved for 1/2 and for 4. And if I look at my list, that matches what my possible zeros could have been. Alrighty, let's take a look at another example. Let's take a look at this example. This example only has 3 terms, but you'll notice that it starts with 2x cubed. So the AC method isn't going to be very beneficial here. So my only option is to start by listing my possible zeros. We want to start with our last term, our constant, which is 9. Factors of 9 are plus and minus 1, plus and minus 3, plus and minus 9. If I take a look at my leading coefficient, I have factors of plus and minus 1 and plus and minus 2. Now remember, we also want to find P over Q. So my possible zero list is going to be 1, 3, 9. Now let's look at our fractions. 1 over 2, 3 over 2, and 9 over 2. To start off, we want to find which value gets us to 0. So I'm going to start off by plugging in 1 into my polynomial. Again, check it with your calculator. You can also just do synthetic division every time and see if you end up with no remainder. It's up to you. When I plug in 1, I do not end up at 0. So 1 is not a 0. Let's try plugging in the value 3. I'm just going to go down the line here. If I plug in 3, here I end up with 2 times 27 minus 7 times 9 plus 9. If I plug that in correctly, I do equal 0. So 3 is my hint, as it is the first 0 that I've found. Let's use synthetic division not only to prove that it's a 0, but to also simplify our polynomial. I've got a 2, a -7, and a 9, but notice I am missing my x term. There is no x term here. So I need to make up for it by putting a 0 in here. Bring down your first value, which is 2. 3 times 2 is 6. Add them together, you get -1. 3 times -1. Add them together. 3 times -3, -9. We get that 0 remainder, which confirms it's a 0, but also simplifies our polynomial, as now we have 2x squared minus 1x minus 3. I now have 3 terms that should work using the AC method. First times last, or A times C, is -6. My middle term is -1. Factors that multiply to get -6 but add to get -1 are 2 and -3. Which means I end up with 2x squared plus 2x minus 3x minus 3. Remember, if you flip that -3 and 2 around, that's okay. You should still arrive at the same answer. We now have 4 terms. We're going to use grouping. If I take out my GCF, I end up with a 2x, which leaves me with x plus 1. I'm going to take out a -3, which leaves me with x plus 1. I've got the same thing twice, so that's how I know my grouping process is going well. My GCF is now x plus 1. When I factor that out, I have 2x minus 3 remaining. If I set each factor equal to 0, I end up with x equals negative 1, and I end up with x equals 3/2. So I have x equals 3/2, x equals negative 1, and don't forget the original 0 you found, 3. If I look on my list, I have 3, I have negative 1, and I have positive 3/2. So it matches the list that I created. So I have found all 3 zeros. One of the activities that we did in class, I had you graph using Desmos. And when you graphed and factored off to the left side, we should have arrived at the conclusion that our zeros match the x-intercepts on our graph. So if I look at my graph, I have negative 1, I have 3, and I have 3/2. Now, you might be thinking, why can't I always just graph it, look at where it crosses the x-axis, and know my solutions? Well, in this case, it does help us out a little bit that it goes exactly through negative 1 and 3 and 3/2. That's not always the case. If my graph was to go through somewhere over here, I don't know where that's going through. So I have to use this process to find exactly where my zeros are. As you work through additional examples and problems, be careful. List all the positive and negative factors when finding your P over Q. And remember that not every zero generated by the rational zero list is an actual zero. In this case, only 3 of the zeros worked. Keep practicing, let me know if you need any more assistance, and make sure to look for other examples out there on YouTube or on the internet.